Hello YouTube! Welcome to part 2 of my movable Glock holster rework series, where I walk you through my approach and design methodology to designing a component to suit a particular custom need. I do this so that those who are interested in doing similar things have a jumping off point. They can at least start learning some of the software or skills or the mere fact that they exist in the year 2018. So, as you saw in part 1, where I just kind of alluded to what I was doing, I wanted to create a MOLLE webbing attachment point for a movable Glock holster, and I had a starting point of a existing component. Now, I've already designed this component in a software called Fusion 360. It's this lovely CAD software that is free for non-commercial hobby enthusiast users, education, and people making less than $100,000 a year. It's incredibly powerful, and I'm not going to explain what the software can do because you can Google for it. What I am going to tell you is that I'm using this piece of software to not only design the component, but also to simulate how it will behave when you put a mechanical load on it. It's a powerful piece of software that lets you explore and understand where the physical stresses are on a component. So let me just walk you through the beginning steps. I've already designed this rosette component that mates with the Glock holster. I've already designed my mimic of the SciTac component. I've created a rigid joint between these two components, and then I've used a combine operation to combine all of these different components together into one solid object and not multiple components. There's only one body under here for those that are familiar with Fusion 360, and using this component I can then go do simulations. Now, for the purposes of simulations, you want to consider disabling any cosmetic features such as chamfers or fillets. Now, you want to disable only the cosmetic features which may impact, only the cosmetic features which will not impact the mechanical performance of the part. Some areas, like this segment here, and the fillets on the radius of the MOLLE clips, the upper MOLLE clips anyways, if I can select it, these guys, I've left those enabled because these actually play a pretty critical role in the mechanical strength of this component. So I have the solid body. Right now it's defined as being made of, no, I don't want to do that. It's being made of Nylon 6.6, which is pretty strong material, but it's not the material that I'm going to use. I've already done a simulation, but let's take a step back here. I'm going to actually... Can I delete results? I can't delete the results. Alright, so simulation in Fusion 360 allows you to do, amongst other things, static stress simulations. You apply mechanical load. These arrows here indicate where that load is, and you apply a set of constraints to the part. It then tells you where your part may or may not fail. It tells you where you might want to increase the amount of material, or whether you can decrease material in other areas. As you can see up here, I've actually iterated this component 55 times to get to this design. It's aesthetically balanced, and perhaps maybe not as strong as I could make it, but time is also a factor in this design. So typically what you would do is you would simplify by removing other components. I'm overriding the design material of Nylon 6.6 with HP Multijet Fusion PA12, which unfortunately the data sheet, which maybe I can put an insert shot here, does not list all of these different things. Poisson's ratio is a compressibility, I guess, coefficient, and HP doesn't provide that. So I'm guessing based on other nylon-like materials. the HP multi-jet fusion is kind of touted as this high homogeneity on the X, Y, as well as the Z axes. Traditional FDM 3D printing, like the printer you can hear in the background right now, the Z axis is usually a little bit weaker under tensile strength compared to the XY plane. However, multi-jet fusion is homogeneous across all dimensions, so I can get away with doing this. Multiple multi-jet fusions in here for some reason. Yeah, so it's a little bit weaker than Nylon 6.6, which has an ultimate tensile strength and yield strength almost twice that of the HP material, around 48 MPa. Regardless of that, I've set my study material. I'm going to define my component loadings. I'm only going to load this piece right here with a 300 Newton force in the upward direction. That's roughly equivalent to 67 pounds. That's way more than I would ever put on a Glock holster. But this is for understanding how the component might fail under extreme circumstances. Like if you got it snagged on something. I'm applying some constraints. In this case, these three faces are constrained on the Z direction, in the upward direction. And these 2 points here are constrained on the X, Y, and the Z, so that this part doesn't rotate or skew in unpredictable manners. Because these little hooks, these protrusions... oh dear. That's not what I wanted. These two protrusions are what interface with the MOLLE web and keep it from sliding back out. So I've defined my constraints, I've defined my load, I've defined my material. My pre-check says it's okay, and I'm going to solve. This is real time. I could solve it on the cloud with a limited number of credits, which costs some money. If you use the Maker license, then it's effectively unlimited credits. In my case, I have a different license which gives me access to other Autodesk software, so I have a limited number of credits. Regardless, solve it locally, and away we go. Now, this is real time. I'm just going to continue talking while it solves. This is a first-gen i7, a relatively simple model, and it's just going to solve it. It's pretty quick. Once it meshes, then it's actually going to apply the load and understand it. This is called finite element modeling. You break this component down into a discrete number of points, and you simulate tensile strength, compressive forces, how it might warp or distort. There's a bunch of complex stuff running under the hood, but for the purposes of... oh, you know what? I screwed up. So this is actually the second time I filmed this video. The first time, all of the toolbars didn't display. One important thing, you want to disable cosmetic features. Go back to simulation. Okay, yeah, now I can solve it and it won't take forever to mesh. Embarrassing demo syndrome, but this is live. More or less unedited. That is meshing much faster. Alright, so you can see here it's giving me this exclamation mark. Safety factor is the design margin for how much additional strength it could take. So if I load it with 300 newtons in this direction, this component could only take 1.181 times that force before stuff starts to crack and fail. But you want to understand why and where. So if we drag this filter down, you start to understand where the part's actually weak. It's weak in these two corners. Now, there are limitations because it's meshing. If you turn the mesh on, you're turning a high-resolution curve of, I believe, 2.4 millimeters into only a few discrete points. So the forces aren't going to be a perfect model. You could do some mesh optimization. I'm not an expert in this, but this is good enough for my understanding. What this says is the part won't fail under 67 pounds of force. However, you are close to the edge of failure. You may start getting some tearing. Safety factor of 3 is a little bit more comfortable. These areas are just on the cusp of failure, especially this hex insert nut might start to tear when you pull upwards. But this hex nut is also reinforcing, so that force is also going to be applied to the underside of this this hex insert, right on here. Okay, so what else can we learn about this? Well, everything under 5, this is where most of the forces are concentrated. All of this other material seems to be relatively superfluous from a mechanical standpoint. If you attack this from the other side, all of this material that's kind of missing is optional. Sorry, all the material that's not shown, that's ghosted out, is actually required. All the blue solid material is superfluous. Now, obviously you can't get rid of the molly clips, you can't get rid of these wings, but you can see here that these supports, all the forces seem to be contained internally. You could shave away material here and reduce the size and weight of this part, and therefore ultimate cost. You could make these a little thinner and you wouldn't sacrifice any mechanical strength. It would look a little bit weird to have this kind of organic shape. And one feature that is coming to Fusion 360 is iterative design, where you can tell it to improve the component and it just changes it for you and provides new geometries. So really, I could cut away these entire spars, these two outer ones, and all the force from this rosette is going to go through this center component into these two clips, as well as through these two spars into the upper molly clips. There's a little bit of force that comes through here, but these middle supports are a little bit cosmetic. What else could I do to improve this component? Perhaps I could move the interface point from these two supports further outwards into the middle of the two clips. Therefore, the forces are going to be spread out a little bit more evenly and is less likely to tear. Right now, all the force is concentrated on this corner, and it may tear open like a zipper down the length of this molly clip in this direction, and over here in this direction. Get rid of that window. Over here, you see that there are some points where the force is a little bit concentrated. In theory, and I guess I should have done this before I sent it out for fabrication, I could increase the diameter of this chamfer. I could make it a lot more of a smooth sweep. I can't make this component any thicker, but it seems like this section here is under a bit too much tensile load, and this is going to be compressed a bit much at the way it's being deformed. So want to kind of consider all these different options. Results, deformation scale. So you can also display how much the part is deformed. This is a exaggerated or adjusted view of how the part might deform. You'll see that this upper molly clip has slid inward or down, and that the actual component where it's being loaded has bent upwards. You can actually see its normal or its real deformation. This looks like it's maybe a millimeter at most. This is pretty acceptable. This just helps inform my decision. I made an alternate version where it's made fully of these hexagons, based on this design where all this material is superfluous, most of this material is superfluous, and all the force really seems to be concentrated in this upper wishbone as well as this lower spar. I made this design where you've got this upper spar mostly intact and all these additional hexagons. The safety factor is a little bit lower. It seems like the force is concentrated on the outer corner, but if you look at the actual material that's below 1, it's very little. So it may fatigue over time under a full 300 Newton or 67 pound load, but I don't really like this almost like a TIE fighter design, even though you're saving a ton of material and a couple dollars of manufacturing costs when you're printing it through Shapeways. I like this aesthetic more, especially once you turn on the final fillets. So this is the design I stuck with. It took me almost 60 design iterations to move these spars up and down, change the points where all these connect, change the diameter of this circle. Ultimately, you can simulate these things many times before you actually spend a single dollar on it. You can understand how it might fail and prevent wasted time and money. This took about 4 hours to design the part, and then another 3 or 4 hours to simulate it many times and redesign it. Again, this is a unrealistic load. If I put a 100 Newton load, which is about 20 pounds, and I simulate it, it should simulate and pass with a safety factor of 3. 20 pounds is more than enough when you're running around, because your pistol typically only weighs about a pound. Now we're just going to wait for this to solve. Yeah, so from a deformation standpoint, it's very acceptable at a normal load. Once you crank up the load, it starts to get a little bit more deformed. I'm going to put a 1,000 Newton or 1 kilonewton load just to illustrate here. Simulate it real quick. I believe that works out to 224 pounds. 224 pounds is like someone literally hanging themselves off of your holster. Something else will break first. Whether it's the strap on your drop leg rig or your belt or the rest of the holster itself. So you see here, there are components under a safety factor of 1. These will absolutely fail. It's just a matter of which part fails first, and as it starts to fail, how does it affect the overall performance of the part? Because if it starts to fail here, then the forces are transferred further outwards. It may just zipper open. These two spars may crack, transferring load to these inner spars, right? This is why I added these inner spars. If these two crack, at least I have a little bit more material here for it to fail onto. If these two weren't here, then all the force would suddenly be transferred down to this seam or this clip, and this would fail and crack open starting from the underside as it hinges upwards. And from an actual deformation standpoint, it deforms very considerably. Again, this is an unrealistic circumstance. You're putting 200 pounds on this. Safety factor of 3. Most of the component is going to pass the muster test. And then from a safety factor of 8, where do we have superfluous material? Again, these bottom two spars are mostly, well, almost completely superfluous, but they're aesthetically pleasing. The middle spars or supports, they're somewhat useful, and the top ones are almost entirely required for this design to work, as well as this material here. So, simulation tool, amazing for understanding how your part may actually fare in the real world before you spend a single dollar to make it. So, hopefully you found this video useful. Don't forget to like, subscribe, comment, hit the notification button, all those lovely things, because the YouTube algorithm is garbage. I don't monetize my videos, I do it for the love of the hobby, and so that other people may learn from this. If you watched till this point, kudos to you, thank you for watching, and the next installment will be actually evaluating the real component after it's been printed. So that'll be in another week or so after it ships and arrives to my doorstep. Thank you for watching, and till next time, cheers.